Okay, and then the exam is going to be 2 hours and 45 minutes exactly, and then after that you will have 10 minutes to upload, like, and it's going to be uploaded as assignment. Okay, there will be a separate assignment which is called exam. Okay, and then you will upload your PDF file. You will make a PDF file by scanning, and then you upload that PDF file as a single file, okay, not many files, but just a single file of all your pages, of your examination report. You just write it down on several pages, and you make scans of that and make one file of it, and then you upload that file as you do in the assignment, as you did in the regular assignment. But that will be, of course, the separate assignment called exam. Okay, I hope everything is clear here. So if there's anybody who's not who doesn't understand what I'm talking about, please ask me. Okay, let me start today's lecture. Okay, so it's the last lecture. So concerning the new material of the last topic. Okay, so the first three. Let me move that away. I think this is sort of okay. The first 3 slides are just a repetition of the previous lecture. Okay, and so let me not go into that. So that's just not. It's there because as a review of the previous lecture. Let me just only talk about a little bit about the last remark of this review part. Okay. Well, we had this stationary, we have the operator, we had this trend, and so on. So we have all kinds of time series in practice, and there is one which is very often occurs in practice. This is kind of financial time series, where in finance people all the time series more or less not stationary. Okay, so this is just no way you can have a stationary time series from the very beginning, just original what you observe, like share price or exchange rate or interest rate. So those things are never stationary. Okay, almost never. I mean, it would be a very weird time series in finance which would be stationary. So most of the time it's not stationary. So to sort of to make a step towards stationarity, what people do, they apply transformations. Okay, and there are 2 popular transformations. This is more or less standard in this field. So the first one is called daily returns. Okay, and this is what you do. You take your original time series, whatever that is. Imagine it's a share price. Okay, and what is it? And then what you make is this, is just xt minus 1. This is just the change of for example, a share price with respect to the previous time moment, and then you divide by the value of previous time moment. It's a relative change. Okay, and it also keeps the sign. Okay, plus or minus 1. It goes up or down. So this thing is never big, right? This is just a relative change, and it's divided also by something. And this change is not so big, and then it's also divided by something, so it becomes even less. That is, and then it could be up or down. Okay, so you sort of make it without a trend. Okay, you sort of remove a trend in a way somehow by applying this transformation, and that thing is called daily return. It has a very nice interpretation. It's a relative change of for instance, a share price. What people also do, they take another transformation, which is log of the ratio of xt and then the share price at the previous time moment, for instance. And then you say, well, why would you take log of that? Why would you take log of the ratio? Well, the reason is that if you just apply Taylor expansion, suppose this ratio is, I mean, xt changes just a little bit with respect to xt minus 1. So it's, this one is close to 1. So then it's just 1 plus something, and that something is hopefully small. And then you apply Taylor expansion, and then you actually recover daily return. So these two are actually close to each other. So they're more or less show the same thing. And that thing is hopefully stationary. That could be seen as stationary in principle. It still could have a trend. That thing still can have a trend. But at least this is something which is more or less, well, hopefully closer to the stationary time series than the original one, because the original one simply contains a trend, okay? And then all kinds of things, also seasonal components. All right, we also mentioned smoothing, right? I didn't do anything with the smoothing. That was one of the methods to, there is a child crying in the neighbors all the time. Disturbing, okay. Anyway, so let's see. So this spline smoothing technique was spline smoothing. That was one of the techniques to estimate the trend, right? And I didn't actually do anything there. I didn't do any specific things. So one of the methods, there are many methods. There is kernel smoothing, and there are other smoothing techniques. And one of the most popular ones is the so-called method based on splines. What is spline? Spline is actually, this is a bunch of polynomials glued together. Okay, so you make a grid, and then on each interval of that grid, you feed a polynomial of degree, say 3. This is the most popular degree in splines. So you take a polynomial of degree 3, and then on the other neighboring interval, it's another polynomial. Okay, so there are two different polynomials, but you have to glue them together in a smooth way. And when you do this, then you create all kinds of you have all kinds of conditions. If you and then by imposing these conditions, you sort of create a bunch of polynomials glued together, and that thing is called spline. Okay, this is what people call spline. This is a very well developed field in numerical analysis. And that thing is very good to approximate all kinds of curves. If there is a function, you can actually approximate that function by spline very well. And you need to put the grid in the right way, and you have to glue them in the right way, and you have to choose the order of polynomials also in the right way. Okay, it's all done, of course, in this common smooth spline. And there is this parameter here, which actually measures the degree of smoothing. What would be degree of smoothing? Degree of smoothing depends, of course, on the degree of the polynomials and also on the grid. Okay, if it's close to each other, then it's going to be less smooth. If it's far away, then it's going to be more smooth. So altogether, this is measured by this parameter. The smaller, the bigger, the smoother. The smaller, the more wiggly. The more wiggly the resulting spline is. And then you just simply try to fit your data by this smoothing curve. Okay, so let's see how it works. So for instance, the sunspot data. So this is the original data, and then we apply a smoothing spline with parameter 0.8. It smoothes too much. Okay, it just doesn't follow the trend at all. And then we decrease a little bit the smoothing parameter, make it wigglier. Okay, and then it follows the trend already pretty well. We can make it even less smooth, and then it becomes then of course grid becomes finer, and then more polynomials. Of course, it will take a longer time to compute, but it's still very fast. And then you could say, well, that's just too much of the following the trend. Maybe I shouldn't, because all these oscillations are also followed by this polynomial. You don't need that. And then probably the choice 0.5 would be the best here. All right. And then once you've done this one, you've done the smoothing, okay, and then you can subtract that smooth thing. That's an estimator of the trend, and then the original time series sunspot minus estimated trend, which is estimated by the smoothing, and then the resulting thing is hopefully stationary. Okay, at least you see that there is no trend here. You don't see any trend at least. Okay, let us now formulate the general notion of a family of models. That's a very important family of models. And it's called moving average models. And this is how we introduce. This is the definition. So we will have moving average, we will have autoregressive, and we will combine them, and all of them are based on the building block, and the building block is white noise. So we always start with white noise time series. We know white noise time series is stationary, very nice. It's the basic one. So there are uncorrelated random variables. Okay, and then this is of course the most primitive stationary time series we can think of. Of course, the constant is most primitive, but it's totally uninteresting. This one at least is random. So the simplest random time series, which is stationary, is white noise. Okay, you cannot think of a more simple time series, and this one is used as a building block for many others. Okay, and what do we then have? We need that as a building block, and from that we build a new time series xt. So xt is equal to this linear combination of the values of the white noise time series. We just go back, just beta 0 times x zt and so on, beta q times zt minus q. Okay, so this is just q values, q plus 1 values of white noise time series. We apply linear filter to them, and there is only q of them which are non-zeros in that filter. So this is nothing else but the linear filter. Okay, and remember we had theorem, and theorem said that any linear filter, nice linear filter, but that one is nice because it's finite, is of course will lead to the stationary time series. So we know it's going to be stationary by the theorem from the previous lecture. And also we had also the covariance function there. Okay, and then if you apply that formula there, or you compute it directly, it doesn't matter, it's also not so difficult. You simply compute the covariance function of this thing. It will take a small effort to do that, or you apply this general formula, whatever way you prefer. You will get that the variance is equal just to this expression, and the covariance function at all the other points. Okay, this is covariance function at point 0, and this is covariance function at all the other points. It's this value for h plus minus 1 and so on plus minus q, and after that it's 0. So it cuts off very, very abruptly. So it's non-zero only from minus q to q. Okay, it's symmetric, so it should be from minus something to plus something, the covariance function, and it's sort of non-zero only from minus from the log minus q to q, and everywhere else is 0. And that's the characterizing property of moving average. So whenever you see autoregressive autocorrelation function or autocovariance function which abrupts, which cuts off from some point, then moving average could be a good candidate to model this time series. Okay. Okay, expectation is 0, of course. We simply take expectation of that, since we start with white noise, and white noise has expectation 0. By the way, it doesn't have to be. If it's constant, it's also good. But without loss of generality, we assume it's 0. Then, of course, the resulting time series of moving average is also 0. Okay, another type of models, autoregressive models. This is more appropriate for financial time series. They like it very much in finance. Autoregressive models, which is also based on the white noise. We start with white noise, and then we also need to define the initial values of our time series xt. Okay, or we run it from -infinity. Okay, I'll explain what this means. Suppose we started from 0, then we need to give values. The first p values. We have to say x1 is this, x2 is that, and so on up to xp. And when you set this, you fix those, and then you have also white noise time series. Then you can apply this formula, and then you define the so-called autoregressive time series. Okay, and this number p, this is the natural number, and this is the order of this time series. Okay, this time series is called autoregressive of order p. This is very important type of time series, studied very well and quite a lot in econometrics literature. It's their thing. They study many of such models. Okay, let's have a look at the particular case. At least this one is sort of not too difficult to analyze. Okay, if you just take p equal to 2, it becomes already difficult. But for p equal to 1, this is everything can be done explicitly. Okay, so just the simplest autoregressive model is the one of order 1. Okay, what does it mean? It means that it should satisfy this equation. Think of that as an equation. So is there a process xt which actually satisfies this equation? We don't want to impose initial condition, for instance. Okay, and then what we can do, we can simply iterate that equation backwards. So xt is something in terms of xt minus 1 and zt. Then of course you can express xt minus 1 as something in terms of xt minus 2 and zt minus 1, and so on and so on and so on. You just go on, and actually you can simply resolve that. This is just infinite thing. Of course, you could say, well, okay, it's formally this thing, but that thing may not exist, because if alpha, if absolute value of alpha is bigger than 1, it diverges, because this is white noise. So it's infinite, sum of infinitely many terms of white noise, and they get bigger and bigger if alpha is bigger than say 1. So no way that thing exists, but it does exist if alpha is less than 1. Okay, absolute value of alpha. So then this simply is well defined. This is some process, and that process is called autoregressive process of order 1, and it is of course, if it's defined like that, then you can simply see, okay, expectation is 0. You can exchange expectation and summation. It's allowed here because this has absolute convergence. And you also can compute covariance of that thing. Okay, you will have to, it will be a double sum. You will have to exchange. Again, a summation and expectation. And if you do that, well, you simply get very nice expression after all. So this is summable thing. This is the geometric series. And then if you normalize that, you simply compute, instead of covariance, you compute correlation. Then you see correlation is even nicer. Okay, correlation is just alpha to the power h. Okay, absolute value h. Of course, it has to be symmetric. And then you see that thing is, well, at 0, this is always 1, of course, as it should be. But otherwise, it's something which goes down. Okay, it's something which gets smaller and smaller, but it's now a 0, so it doesn't cut off to 0 compared to moving average. So the covariance between xt and xt plus h is always non-zero. So there is always an exchange of information between these two. So there is, and moving average, it cuts off after some. There is no memory, and here there is infinite memory. You could think of that. So that's why it's interesting. So this time series has an infinite memory. So the xt still keeps some information from very, very long ago, although it's decreasing, it's exponentially decreasing, but it's never zero. Okay. What people do then, they say, oh, we don't like that idea that it's infinitely, autocorrelation is non-zero, infinitely long, actually never zero. Then they came up with this different type of autocorrelation function. Okay, so that's called partial autocorrelation function. It's actually, it was invented for the sake of autoregressive models, basically. So it's a bit difficult thing. I don't want to go into that. It's also mentioned in the lecture notes, but also didn't exact definition was not given, because for exact definition you need to introduce the notion of orthogonal projection onto the linear subspace of Gilbert space spanned by random variables. You have to introduce a Gilbert space of random variables and then introduce orthogonal projection operator on that space, and so on and so on. And then this sum operator, which, okay, intuitively what it does is this. It's a correlation between xt and xt plus k. So this is the partial autocorrelation at lag k, right? It's a correlation between xt and xt plus k with the influence of zt plus 1 and so on, zt plus k minus 1, everything in between xt and xt plus k removed. So by subtracting that projection, we sort of remove all the influence of the time series in between xt and xt plus k. So it's a pure correlation between these two. And if we do that, then the resulting partial autocorrelation thing will cut off. Okay, it will be exactly what we would want to have. Okay, what we have in moving average, but we don't have that in autoregressive models. But if we just adjust the definition, we sort of consider another definition. That's why this thing is introduced. Okay, this is only for the sake of autoregressive models. It could be computed. The estimator is for that thing. It can be computed in R. We will come back to that. Okay, let's just do the following. That's we have an expression for xt. Of course, we can write down expression for xt plus minus h. Right? No problem. We can do that. Just suggest this formula instead of t. Use t minus h. And then the expectation of that thing is 0. Okay, we know that. And then we can multiply xt and xt minus h and take expectation of that. And that would be, on the left-hand side, it would be the covariance function at lag h. Okay, that's exactly what we do here. Well, why not? I mean, we can do that. This is just, we're simply manipulating with the expressions of the autoregressive model. So there is xt times xt minus h. This is equal to this sum. Okay, we can simply write down, because there is expression for xt and there is expression for xt minus h. And now we're taking expectations from both sides. Okay, just by definition, this is gamma of h, right? It must be gamma of h. This is a covariance function at point h, because there's a lag here, h, t and t minus h. This has a lag between them, h. And if it's a stationary, then of course it has depend only on h. So it's gamma of h. Okay, what happens here? Well, here we have alpha 1 times expectation of these two, but this is, we need to compute, it's also gamma, but at what point? Well, this minus that. So it's h minus 1, right? So it's gamma h minus 1 and so on. And the last one is h minus p. So h minus p. And there's alpha 1, alpha 2, and so on. So we get this sum. Okay, and then there's last term. That term, expectation of that term is either 0 or not. Well, it's only non-zero if if h is equal to 0, right? Because we have here xt, and then there is zt here. If we multiply with zt, then there is only one thing which depends with which it correlates, because all those, they depend on the previous z's. Okay, so if you multiply this with zt, okay, and then you take expectation of that thing, then everything here will be 0, but it's going to be zt squared, and expectation of that is sigma squared. Okay, so it's exactly what we get here. So only for one case, when h is equal to 0, we get an extra thing. We get here is sigma squared. Okay, so what did we get? We get actually something which always true. If our model is autoregressive, then this has to hold. How we should see that? Well, this is something, this is some equation, some identity in terms of autocovariance function gamma and sigma squared. Sigma squared also plays a role here. So it must be true. We just derived that. That's called Yule-Walker equations. Okay, what we can do next, we simply can normalize the whole thing. We divide both expressions by gamma of 0, which is a variance. And then we will get here autocorrelation functions instead of gammas, right? So then you will write just rho of h, and then the same equation remains. We just simply normalize it. We just divide it by gamma of 0. Here we just get 1, and then we can express sigma squared. We can resolve this with respect to sigma squared. So this is what we will get. Here we, well, we basically, yeah, this is what we will get here, and that's it. This has to hold true all the for each time series, autoregressive time series. That's called Yule-Walker equation. They're kind of nice. That doesn't take a lot of effort to derive them, and we know for sure that if we have autoregressive model, then this has to hold. We will use this later on. Okay, let us rewrite them in matrix form. Okay, let's just write rho as a vector. Okay, let's write alpha as a vector. Let's introduce the matrix R, which consists of these rows. Okay, so matrix Rij, the element Ij, it's a symmetric matrix, and we put, depending on this difference here, we put one of these rows in this matrix. Okay. And it must be symmetric because you just exchange E and J, you will get the same number. And then we can rewrite this. So here we have a whole bunch of equations. We can, instead of that, we can rewrite just one matrix equation. So rho is equal to R times alpha. So what is the equation? What is here? Well, rho is on the left-hand side, and rho is also in R, because R is based on rho. So rho is the autocorrelation function, and it is present here on the left-hand side. It is also present in the matrix R. And there is alpha, which is a parameter of our autoregressive model. So this has to be true. And well, the same here. We simply can express this sum here. This sum here is just the vector alpha times vector rho. Okay, so it's just scalar product of these two vectors. This has to be true, and it's called Yule-Walker equations in the matrix form. Later on, we will use them for estimating. This is very nice feature of autoregressive model. Okay, now we can put these two together. Let's just combine moving average and autoregressive models. Let's just mix them together, and then we'll get a huge family of models. Okay, so there is a part which comes from the autoregressive model, and there is part which comes from the moving average model. Okay, so that thing. Okay, think of this as autoregressive part, and think of that as a moving average part. Okay, but well. Then, of course, again, you need initial values of x, and then you have white noise as a building block. And what do you need to specify more? You need to specify the order P, okay, P, how many lags you go back in the autoregressive part. And then you also need to specify Q, how many time lags you go back in the moving average part. And that defines a so-called autoregressive moving average time series of order PQ, okay? So how many parameters we have here? Okay, we have P, Q. These are two parameters, and we have alpha 1, alpha P, and we also have beta 1 and so on, beta Q. Okay, beta. There must be beta 0, but we say okay, let's put that always 1. Without loss of generality, we can put it always 1. If it's not 1, then it has to be non-zero. And then we simply divide by that, and then we can make it 1. So we can always adjust this series by dividing by beta 0, which is present here. We divide by this beta 0, and we can always reduce to the case when beta 0 is equal to 1. That's always possible. So therefore, it's not present in the model formally. Okay, and then you can go further, actually. We are not going to treat this class at all. But in principle, what we can do, we can say, okay, imagine the time series xt such that if you take, if you apply d times the difference operator, you make a difference, that thing which is here is ARMA. Okay, then xt is ARIMA. Okay, so if the difference of order d is ARMA, that defines xt as ARIMA. Okay, so we have to go from differences to the xt. That means we are sort of integrating, because taking differences is sort of differentiating. Okay, this is the idea. So we need to integrate, and that's why it's called ARIMA. And then of course it's more it's a generalization of that one. If d is equal to 0, then you're back to ARMA, but otherwise you can also make it even more difficult. Okay, then you have 3 parameters here, P, D, and Q. Of course these alphas also and these betas are also need to be specified as well. So that's called ARIMA, autoregressive integrated moving average. Okay, now very important remark. This is something very important for exam. Okay, there is that could be that you have a question at the exam where you get a certain time series, okay, and then you're asked to say whether this time series is ARMA or not. Is it autoregressive moving average time series or not? Okay, and here's an example. Okay, let's just have a look at this time series. Xt is equal to xt minus 1, 1/2 xt minus 2, plus 2 zt plus 1, plus zt plus 4 zt minus 1. Okay, and then you look at this. Here's the definition, and here's the process. You say, well, no, it's not ARMA, because here's I see zt plus 1, but it has to be zt here, and it has to be 1 here. But the question would be like, is there any multiple of this xt ARMA, so that you can multiply with some constant so that it becomes ARMA? Okay, you could say, okay, I can divide by 2, then I can make this 1, but still I have here zt plus 1, whereas I have to have it here zt. And then you say, no, it's not ARMA, but it's wrong. It is ARMA. Why? Because you simply can redefine your white noise process. You could say, I introduce a new white noise. I say zt prime is equal to zt plus 1. Okay, you could do that. Then actually I can redefine it even to observe this too, but okay, let me not do that. To observe that constant too by changing this sigma squared. But anyway, let's just not make it more complicated. So I redefine a new white noise, And that new white noise is actually also white noise. I mean, it's just shifted. So what's the problem? ZT prime is also white noise. Everything remains. It's still uncorrelated. It still has sigma squared. So this is white noise. And then I can rewrite this in new terms, okay, in the terms of my new white noise. And then it is ZT now, okay, ZT minus 1, ZT plus minus 2. Now, yeah, I divide by 2 the whole thing, okay? So this I divide by 2, so I have my new time series ZT prime, which is my original one divided by 2. And then I should write down, of course, in terms of my new x, okay? So I divide by 2. And then I rewrite everything in terms of my new white noise. And then I see what the resulting thing, and now I am satisfying this definition. It is ARMA model. And okay, with what parameters? Well, 2, because I have 2 here and 2 here, and I also can specify alphas and I can specify betas. So for that one, okay, for already, so indeed, xt divided by 2 is ARMA, with parameters 2, 2, and with this alpha and with these betas. So pay attention to that. Is something of that kind. At the first glance, it doesn't look ARMA, but it is ARMA if you divide it by 2. Okay. Okay. Let's see. Maybe we can have a break. Let me see. No, not yet. Okay, let's see what is next. Okay, well, just one example here. Well, actually what I did, and it's all done in the script file, just run it. It's fun, actually. There are nice built-in functions in R for simulating moving average, autoregressive, and ARMA. You can simulate them and see what they are. Actually, well, I tried many of them, and I still do not, I mean, I don't know, if you see something like that, is it moving average or autoregressive or ARMA? I don't know. But I do know that it's a moving average because I simulated from moving average with these 2 parameters. Then it looks like this. Then I simulated autoregressive, and it looks like that. And ARMA looks like that. But still, I mean, if you just see something and I don't say what I simulated, then you wouldn't be able to say whether it's autoregressive or moving average of ARMA. That's just no system there. So they look arbitrary, more or less. It's always something like that, and it just goes up, down, and it could be less wild or more wild depending on all these parameters. Okay. Okay, I think we can, let's see, yeah, I think it's a good time to have a break now. Let's have a break for 15 minutes, and we'll start at 14:31, okay? So let's have a break. And please go ahead and ask questions in the chat if you have any. Let me stop sharing. So, okay, I see. I will have a look at the chat now, and you have a break. Okay, let us continue. I recalled what I wanted to say at the very beginning. I wanted to say it now because this is important. Those students who have don't have conditions to make an exam at home can apply for possibility to make it at the university, but you have to do it 2 weeks before. Okay, so I want to announce that. So if you if there is no if you don't have facilities at home for some reason, or you don't have conditions for some reason, then you can make examination at the university, but you have to apply for that with the exam organization 2 weeks before. I think we're still on time, so please take that into account. I hope that's not needed. I mean, I would prefer to make exam at home, for instance, but who knows? Maybe some people would prefer to make an examination at the university, and that possibility will be provided, okay, upon request. But you have to make that inquiry 2 weeks before. Okay, here's this question about gamma. Okay, that's somebody has already answered that. Gamma of it's a symmetric function. Another one is why do you not divide the first two x terms also by 2? Let me share the screen. I actually glad that somebody asked that. So this is very important. This is a small detail which is important. Okay. And actually, this is very typical mistake in the exam. Okay, this is really typical exam. So you see, let me write it. The thing is that because if you divide by 2, then you will get xt divided by 2, not xt prime, and you have to express everything in terms of xt prime. Okay, I hope. Let me see whether I can I do that here? Write it down on the screen. Some reason I can't. Is it clear to everybody, or I need to write it down? Let me show this. So you see, we divide xt by 2. Okay, this is my new xt prime. Okay, and then I have here xt minus 1 divided by 2, but I have to express everything in terms of xt prime because this is the definition of the ARMA model. I have here xt, and then there must be the same xt on the right hand side. So if I write here xt prime, then I also have to write xt prime here, and that's exactly my definition. So when I divide by 2, there's nothing happens to the coefficients here, because the coefficient 1 remains 1, because xt divided by 2, it's xt prime. So xt prime is here, and there is xt prime is here. So this coefficient doesn't get divided by 2, because I need to express everything in terms of xt prime. This is very typical mistake in the exam. Okay, people do the following: they divide, and then they write here xt divided by 2, and then they say, well, it's xt prime, but they leave xt here, and they divide by 2 the coefficients here, and then they put those coefficients here, and then they say alpha 1 is equal to 1/2, and alpha 2 is equal to 1/4, which is wrong, because it has to be the same xt. Since I've already made a transition to xt prime, I have to express everything here also in terms of xt prime. That's the definition of the ARMA. Okay, I hope this is clear. This is very important because this is a very typical mistake in the exam. Okay, another question was, let me see the chat. Can you also transform a time series of moving average if it contains? That's a sneaky question, because that's exactly the question in the assignment. Well, I hope you should figure out what I explained here. You see, the thing is with this white noise is always white noise if you just if it's just shifted by whatever time lag, it will remain white noise. That's the property of white noise. That's a good thing about white noise. It's not always the case for other processes. If you redefine a process by shifting the time lag, okay, you can always reshift. I can introduce a new time series. You might change something in that structure, and maybe something will go wrong. But for white noise, it doesn't go wrong. It remains being white noise. Okay, so I'm not going to tell any more on that. Hope this is clear. Okay, so this is the the simulated examples of moving average, autoregressive, and ARMA. Okay, and then you can play with that. It's actually fun. Although, I mean, it would be nice if something nice would come out, right? Some nice picture, or whatever. It's not. It's never nice. It's something very wiggly, and it's not like, for instance, fractals. You know, you simulate fractals, then you get some nice pictures or some patterns. In probability theory, for instance, you want for some percolation theory, there are some nice pictures, but I think that's not the case here. Okay, anyway, here's a very important part. Okay, suppose we observe a time series and we know it's stationary, at least, okay, we assume it's stationary. And it has a known mean, okay, and an unknown covariance function. We know it is autocovariance function. It should depend on h, and we know it must be the constant mean. It shouldn't change with the t because it's stationary. So how can we estimate those? Well, as to mean, that's very simple. We simply take the average of all the observed time series values. That's it. Just as many as we have, we just sum them all up and we divide by the total number, just sample mean. And in fact, that's it. There's nothing more to it. That's very simple. And unless you assume any other things, if you just don't assume anything, you assume only stationarity, that's the best you can do. That's it. That's the end of the story. And it has to be a good estimator, because if it's a stationary, then that thing should converge to the true mean, the one which is the deterministic value of our time series, the deterministic expectation of our time series. Okay, and one can prove that is even that this just converges, and that's the best you could do. And it's very simple, fortunately. What about autocovariance function? Okay, what do we do there? Well, we know what is the autocovariance function. This is just expectation of xt minus expectation times xt plus h minus expectation. That's just definition. What do we do to mimic the expectation? Because this is the theory. The theory says it's expectation, but we cannot take expectation because we don't know the distribution. But that's just what it is all the time. If you don't know the distribution, so you cannot compute the expectation, you simply substitute that by taking the empirical average, empirical mean. That's it. And this is what we do here. We know that it doesn't depend on t. So the covariance function is always the same between xt plus h and xt, and we can run t as long as we want, as long as there is the same time lag between these two observations. So what we're going to do, we're going to take xt minus expectation and then xt plus h minus expectation. Okay, they're far apart by h, And then we run over all t's for which this is the case. So we run over all pairs for which we have the leg h. And then we simply take an average over them. That's it. And that's also the best you can do. So it has to be a covariance function. We know it doesn't depend on t, so we run over all t's as long as we respect the lag between the xt and xt plus h. So it has to be kept fixed, the lag. But t itself can run as much as possible, and we can run it from 1 till n minus h. Okay, so there's this many possibilities. In principle, we should divide here, but 1 divided by n minus h, but we divide by n. Why? I don't know. There's just a tradition. People do that. So in principle, the true average would be 1 divided by n minus h, but instead use 1 over n, and it's more or less close to the true mean if n is big relatively to h. H is usually much less than n. N is much bigger. We have n is as many time series observations as we have, so it could be a very long time series, and h is usually small. Okay. Well, relatively to n, and then these two things are close. Okay, once we have that, we can of course normalize. We also have gamma of 0, right? That is also here. And what we can do then, we can normalize by gamma hat of 0. Simply divide by gamma. That would be an estimator of the autocorrelation function. And then of course the first one is going to be 1. The perfect estimator, right? Because we know that the theoretical one is also 1. So at least at one point we will be able to estimate perfectly. Well, but for the other ones, it's going to be some estimator, and that's it. And they're of course going to be biased. And that sample autocorrelation is called correlogram. Okay, you might hear this fancy word. So and now you should know that this is nothing else but just a sample autocorrelation. Okay, you assume that your time series is stationary, then you apply this very basic idea of averaging things, then you can compute a sample autocovariance, and then you normalize that, and then you will get sample autocorrelation. And correlogram is nothing else but just a fancy word for empirical autocorrelation function. That's it. Okay. Now you have time series. You never know whether it's moving average or not, or it's ARMA or autoregressive. If it's true, if it's not simulated, okay, then of course you never know from which model it comes. It may not come from any models we know, but you would like to model your time series as coming from a certain model. Then you could look at its correlogram, and if you see that correlogram cuts off after lag q, then you say, okay, if under stationarity assumption and assuming that my estimator is good, that means maybe my time series is a moving average. Okay, and you see it cuts at lag q, then you say, oh, maybe moving average of order q is a good model for that, for this time series. The same, you could do the partial autocorrelation. You could estimate partial autocorrelation function, okay, and then you could see whether it cuts or not after some time lag. And then we know that the theoretical partial autocorrelation must cut for autoregressive model of order p, for instance, and if it cuts off outside of a lag p, then you could say, well, maybe my true time series is coming from the autoregressive model. Okay, that would be the idea. So this is a useful tool to sort of to decide what would be then an appropriate model, moving average or autoregressive, by looking at the correlogram and by looking at the partial autocorrelation function, empirical partial, the estimator of the true one. Okay, let's come back to our Yule-Walker estimators. Remember, we had this, remember, let me just remind you, we had this equation. It's just true. If we have autoregressive model, it must hold. So what do we have now? Now we have estimator of autocorrelation function. That means we have here numbers. We have rho hat, and we also have r hat, because this is also, it also depends on rho. So this matrix here depends on rho. If we have rho hat, then of course we have r hat, matrix r hat. So this one and that one, they are determined as an estimator. And then we can actually resolve this equation with respect to alpha. So we can multiply with r to the power minus 1, and then alpha is equal to matrix r to the power minus 1 times rho, okay, from here, just from here. And then if we have rho hat and r hat, then we will have alpha hat, and the same with sigma. So we have gamma hat, we have alpha hat. Alpha hat is here, okay, we get it from here. Then rho hat is also we have. So we have gamma hat. That's exactly what we're going to do here, okay. So we have gamma hat of 0. We have rho hat. Substitute them, and we can get alpha hat and sigma hat. And that's good. This is just because if we have autoregressive model, this must be true. And then in doing so, we get a just very concrete and analytic form of the estimator, and it's called a Yule working estimator. And that estimator, if your true model is indeed autoregressive, that estimator is good. Okay, so it's always because theory says it must be the case. It must be the identity here. Of course, we don't have the true R and we don't have the true rho, but these are good estimators of the true R and the true rho, and therefore alpha hat is also a good estimator of the true alpha, if there is a true alpha there. Okay, this is of course very much specific to autoregressive models. That only applies to autoregressive models. A small step aside from that, that's it. That just breaks down. Okay. Of course, that's not the end of the story, because there are many other models, methods to estimate parameters. Of course, this is only for autoregressive models. Imagine we have moving average. We can always rely on maximum likelihood. Okay, what is maximum likelihood? We will have to specify the distribution of the innovations of Zs. Usually, people assume they're normal. Okay, they're independent normal with zero expectation and variance sigma square. And then you have a likelihood function. Okay, you can write it down. It's going to be a complicated thing because it's not a product anymore, right? So it's product only for independent ones. They're not independent, but there is an expression. You see the dependence, and you can, in principle, write down. It's a horrible thing. Okay, it's analytically you can write down the likelihood, and then you get very complicated likelihood, and you can maximize that likelihood, and it's always done by numerical procedures. And then you can get estimators for your parameters, okay, betas for moving average, or alphas for autoregressive models, or for alphas and betas for ARMA models or ARIMA models. And then so maximum likelihood doesn't say anything about the estimating the order. Okay, order is something different. It's also a problem in itself. You specify the order. You say, okay, give me maximum likelihood for P equal to 2 or Q equal to 3, for instance, and it will give you, okay, and you see, oh, is it a good feed or not? And then this is an additional problem, choosing the right order of the model. Okay, there is another thing, which is the goodness of fit. Okay, I have my time series. I believe it's ARMA, okay, with these parameters, let's say 2, 2, okay. Order 2 of autoregressive, order 2 of moving average. But, and then what? Then it means that it's sort of generated in a certain way. it's sort of based on the white noise. So what can I do to check that? Is it actually true what I think? I think it comes from ARMA, but is it actually true? Can I check it? Can I actually, by looking at the data, check the goodness of my ARMA fit? Okay, first of all, I assume that model, okay, and then whatever, usually it's maximum likelihood, and then I apply maximum likelihood method to estimate alphas and betas, okay, and then I have alpha hats and beta hats. Okay, I also account for possible average, which may not be 0. I can estimate mu hat, which is not a problem, right? This is just the average of the whole thing. Then I sort of center that, and then instead of x's, I take xt minus mu hat, and then I'm sort of, okay, I have my alphas, I have my time series. I can actually estimate my white noise if there is a white noise, and these are called residuals. Actually, I'm doing the same thing what I did in linear regression. I was also estimating first parameters, and once I estimate parameters, I can also kind of estimate the noise, okay? And that's called residuals. And by looking, and I know residuals must be normal. So by looking at my residuals and comparing them to the normal ones, I can say whether my model is good or not, whether it fits well or not. The same here. I'm trying here to estimate the white noise, and I know it must be white noise. So they must be uncorrelated and have the same variance. Okay, I can compute them by running my ARMA backwards, by running that with respect to the white noise rather than xt, because xt I have, alpha hats I have. So I now express my so-called white noise estimators, which are residuals. I can estimate them, and then what is the idea? And the idea is that, okay, if my model is good, then they have to be close to the white noise. And I know that correlogram of the white noise is actually, it's a mathematical fact. It behaves like normal with parameters 0, 1 over n. Okay, that's it. This is what, if it were white noise, then correlogram of white noise is simply normal random variables 0, 1 over n. Okay, so those things, the correlogram of those, the sample autocorrelation must also behave like the one of white noise. So among other things, I need to see that my correlogram never exceeds 2 times variance, or 2 times standard deviation. Okay, variance is 1 over n. So standard deviation is 1 over square root of n. So it must almost never, okay, hardly ever exceed this value. So if I now compute these things, then I can, of course, compute its correlogram or sample autocorrelation, and that this should not behave too wildly. It should actually be most of the time close to 0. It should not exceed this value. Okay, the autocorrelation, the sample autocorrelation function of this, and that's it. This is the basic fact. It's actually not nothing else. It's a very simplistic approach, so this idea, this fact, is the basis for two tests. It's called Portmanteau test, Box-Pierce test, and Lewin-Box test. They're different, but they are based on the same idea. And that idea is just this, okay? That the sample autocorrelation of my residuals has to be close to the sample autocorrelation of the white noise. That's it, nothing else. So it is based on a rather limited property, okay? Not on one hand. On the other hand, it's good to base it on a limited property, because it makes it more stable, it makes it more robust. So the less you use, the more robust your test is. but of course that test is less reliable, okay? Has less power. That it's more reliable, but it has less power. So these two tests are based on that, and you can check the lecture notes for details about these two tests. Okay, let us just finalize things. So this moving average, I generated myself. I know it's a moving average. I just generated this time series, okay, by using moving average model. And I've chosen this parameters value, beta 1 and beta 2, and I've chosen this sigma squared. Okay, and then I had a look at the sample autocorrelation function. Of course, it's 1 at 1. It has to cut off after 2, right? That's just how moving average is, at least the theoretical one. And okay, it is kind of the case, although this one goes slightly above what, I mean, there, after that, they're sort of small, okay, it's 0. What, I don't know, 0.2. So they're all below 0.2, only the second one is bigger, it's around minus 0.5, the autocorrelation. It's sort of okay, so sort of my sample autocorrelation is kind of as it should be theoretically, but if I use maximum likelihood and I estimate beta 1, okay, and you know, I know this, I generated it from the normal white noise, and you see how difficult this model is because the maximum likelihood is actually not good. It's not doing a good job. So this is my true value, and this is what it gives me. It's even a bad, gives me a bad sign. So beta 2 is a bit better, but also just not so good. Sigma, okay. So the maximum likelihood estimates are not good. Even I know it's a moving average. I generated from there. So this method simply fails. Okay. Okay. What about this goodness of fit? Okay, goodness of fit is okay if I apply Ewing-Box test, and my H0 there is the model fits well, okay, and it should, because my moving average, I know moving average, I generated from moving average, my time series is truly moving average, okay, at least that is okay, at least that is confirmed. So p-value is big, that means I do not reject H0, that the model fits well, so the fit is okay, but the estimates are bad. Okay, what about autoregressive? Autoregressive, somehow things are better, especially walking estimates. So my true alpha is minus 0.9. You have a look at the script file, run it yourself, try to play with parameters with orders. Okay, it's order 1, but take order 3 or 2. You will see that your walking estimates are good. You see it as the estimate alpha 1 is estimated pretty good. Sigma squared is also a good estimator, so they're rather accurate. Okay, the sample partial autocorrelation, it must cut after 1, and it does. Okay, so everything is fine here. So this is the first value, and yeah, partial it's not 0 only at 0, and everywhere else is 0. That's it, and sort of course, it's not exactly 0, but these are small values. Okay, at least they're all within plus minus 0.2. Okay, let's have a look at the ARMA, but we know already things are pretty bad in moving average, and ARMA, of course, contains a moving average as an ingredient. So that means that we shouldn't expect too much of the ARMA as well, right? So we have ARMA now with alpha 1, alpha 2, beta 1. So it's 2, 1. So we have two moving averages, 2 moving average coefficients, and autoregressive coefficients, and 1 moving average. And then we have sigma. Okay, again, employing maximum likelihood. Again, you see things are pretty bad, even for autoregressive part. If it were just autoregressive, we would have done better, but since there is moving average in it, and moving average sort of spoils the whole thing. So they're all not really good. Okay, they're not too bad. Well, they are bad actually, but at least not as bad as for only moving average. Okay, if we just have a look at the sample autocorrelation function, what should we see? Well, we should see of the residuals. That means we are now looking at how our test for goodness of fit test should perform. So we should expect that we shouldn't, of course, it's at 0, it's 1, that's just by definition, but everywhere else it should be small, and it is, okay, at least this part is okay. So, and indeed, if we just look at the Porte-Monod test, it will give us a value of 0.457, which means we do not reject H0. H0 was the model fits well. At least that thing is okay. Okay, what can we do next? And in fact, this is what is of the most interest for practitioners. For practitioners, of course, you just fit the model, okay? You sort of believe in that model, okay? I suppose I believe in this model. My time series comes from ARMA 2.1, okay? And what did I do then? I estimated alpha 1, alpha 2, beta 1. I estimated sigma, so I know everything about that model. Now I can run this model forward, right? I can predict. In principle, you could do it yourself. ARMA is just a specific expression. Everything is specific there. And now you have alphas and betas. You just run it forward. You can predict. And that would be your prediction, okay? And this is what people are interested in. They want to predict and see what would be in future. And that's very interesting. For instance, for like the prices of shares, you would like to know what it is going to be in a week. And then I can now make a decision of say, selling or buying certain shares. Well, and that you could do by predicting, but of course you have to believe in that model, and it has to be the right model, okay? And that's either you do it yourself by just running this ARMA formula, or you just say, well, I use ARMA with these alphas, and then you just use common predict, and you could have a look at the predict point ARIMA in R. It has a lot of possibilities. Okay, still we didn't touch upon a very important question of choosing the order, because of course I say 2-1, but who says it's 2-1? There are so many possibilities. It could be 1-2, right? It could be 2-2. So how should I choose those? Well, it could be chosen by using AI criterion. It's again, we are now in the field of a little bit of sort of ad hoc things. There is a theory there, but again, it's based on the fact that the true model is indeed ARMA, but you never know that in the practice. So at least there are methods for choosing orders as well. Among others is AI criterion. Okay, we are done. Let me stop share. Today, okay, there are no questions. Okay, remember I said that if you need, if you want to make exam at the university, please apply to this examiner organization 2 weeks before the exam. I will put practice exam within this week, by the end of this week, and also instructions for exam. I will put 2 practice exams with solutions, and remember that you will be allowed to use 4 pages for your exam during your examinations. Okay, that's it for today. And unless you have questions, I will wait for a little while. But otherwise, we are done for today. And next time is going to be a practical session as usual with the 3 TAs. Now we have 3 TAs. There will be 3 sessions, and they will they have this system with the making appointments. Some sort of you make a reservation in the well, and you're supposed, of course, to start the assignment 4. and then so that you have questions, and then and the last 10th of December we'll summarize the whole thing, and there will be question hour, and I will talk about exam also. Okay. Question for the assignment: do you mean to get a formula for the trend as well, or can we just use decompose in R like in the script? Decompose would be fine, I think. I don't remember how it was. Let me check the. Let me check the segment 4. Where is it? For myself to see how it is, to recall how it is formulated. Let's see. It's question 4, the assignment. Question 4. Okay, plot the trend. Yeah, I think decompose would be. There are many possibilities indeed. Compute trend, plot trend. Moving average, yes. Well, okay. One of the things you need to do, okay? Choose the one you prefer, but do it correctly. And then one method would be good. Any method which is appropriate there. If it's sort of not appropriate, then you shouldn't be doing that. But otherwise, any of the methods we discussed can be applied. And if you just do it in the right way, that would be good. That would be full, complete answer to that. Okay. So any other questions? Okay, 4 times, yes, 4 times A4. Yeah, 4 sides. So just 4 pages of A4. So basically these are 2, 4 sides. So these are basically 2 physical pages, both written on 2 sides, but you can make them 4 on one side. Well, we'll not be able to check that, I guess. Look, I say 4 pages, that's it. So I'll just stick to that. There is no need for more than that. Believe me, this is just going to be distracting only. You don't need too many things. 4 is more than enough. You just write down the necessary formulas. There are not so many of them. You don't need to, for instance, to remember to know the quantiles or whatever. There will be a lot of information in the assignment itself. Okay, or in the exam text itself, and then just basic things like confidence intervals, tests. What else? You might write some of the examples, maybe, I don't know, some of the examples for instance, working out a certain distribution belongs to exponential family, for instance, just to sort of to remind you what is the definition of, okay, for instance, the definition of the exponential family will be in the exam text, so you don't need to write that down. I will simply put it in the exam, but maybe an example of how you compute, how you bring it to the exponential family, something like that. Okay. So we can use LS, for instance, polynomial of degree n, least squares. You didn't get it decompose. What did I do? I will not tell, but well, I did do decompose. Look, it doesn't have to be good, actually. I mean, it shouldn't be too bad, though. But I mean, you cannot expect it to be perfect because it's a real data, isn't it? Yes, it's a real data, so you cannot expect that things are perfect. But you can do also if you see that it's better, then decompose. Why not? But then you have to choose what the degree of polynomial and so on. There's a lot of things here. Didn't get it. Decompose was okay or not. Decompose is okay. If you use decompose, it's okay. All right, that's it. We are done, I think, right? So I will close this session unless you have more questions. Okay, polynomial degree. Okay, thank you very much for being here. I'm closing the session, and please go ahead and make assignment 4. And once again, I'll make sure that the practice exam will come online shortly before the end of this week. Okay. So for the question 4, we are not supposed to give an equation, just a plot for A. Let me check again. Estimate trend and seasonal component for this time series. Let me see. Well, it's indeed true that I don't say you need to give a plot, but I do give a plot, so it wouldn't hurt to give a plot. So formally, you're right that it's not asked, but that would be good to give a plot. It shouldn't be too much effort, right? Just give a plot to demonstrate the how good your estimator is. Estimate trend and seasonal component for this time series. I would say just give a plot, because this is, I mean, otherwise, how do we see that you did the how that your estimate is reasonable? How that it's what it's supposed to be? We need to see the estimate itself. Okay, so the only way to demonstrate your estimator is by producing a plot. Okay. Thus, no equation required. Do I understand it correctly? What kind of equation? There is no. I'm not. No, equation is not required. You need to, of course, to explain what is your estimator. Okay. I don't know what you mean by equation, but you need to specify what your estimator is. If you mean by equation this, then you need equation. But I don't think you need to write down equations. You just need to write down the definition of your estimator. You need to explain what is your estimator. We need to understand what it is, whatever means you use. So you say, I use this estimator, and it should be clear what is that estimator. And then you plot it to see how it actually performs. What is the resulting, how it looks. Okay. You do need to explain what the demonstrate what is the estimator that you use. Okay, if you just give a plot and then you say what plot of what, okay, you do need to explain that. Okay, I hope this is explain that. That's it. So let me close the session for today. So thank you very much, and we'll see each other on 10th of December. Okay.